Calculus class, and see if we can get a relatively good picture of this graph paper. And I'm not certain what this lovely little thing is up here. I wish this would go away. Now that's be gone. All right. So we're looking at section 2.1. It's the first information we're going to cover right out of this textbook. And we're talking about rates of change. And tangents to a curve. And I am taking this title verbatim from the textbook. Okay, verbatim from the textbook. Let me see if I can zoom out a little bit and see if it might pick up a little more of my handwritten work. That's not really so good even yet. I don't see that it's doing anything. All right, technical difficulties. Okay, all right. Before we really jump in here, we're going to take a very basic algebraic review, and this might seem like baby math to you, and that's great if it is, but it's definitely information that you'll need to recall and be good at as we move forward into the concept we're going to be writing about. And the first thing we want to talk about is how to write the equation of the line. How to write the equation of a line, of a straight line, or what they would call a linear equation. How to write the equation of a line. Okay, so to write the equation of a line, we know how to do this, and the way we do this, or in general the way we most commonly do this, is by using what we call the point-slope formula, which means you need to be given a point and you need to know the slope of the line in order to write the equation of the line. And that formula is y minus y1 equals slope times x minus x1. So it requires that you have a point on the line and you know the slope of the line to therefore write the equation of the line. And one of the big things we'll be doing this semester is writing the equation of a tangent line to the curve. And a tangent line is a linear line, a straight line. You need to be very comfortable and confident with coming up with that equation, and you're going to need to use this formula repeatedly to make that happen. So an example would be, suppose you want to have the equation of the line that's passing through the point, say, 2, 5. So your line is going through this point 2, 5, and you know the slope of the line is say, negative 5. So they say, what is the equation of that tangent line, or the equation of that line that's going through that point, and we know its slope is negative 5. Then we go ahead and we go to this lovely formula, which is probably etched in your head from having been doing algebra for many years. And so y1 is the 5, m is the slope, and x1 is the 2. So this is the point x1, y1. So you just replace the x1, y1 variables in the formula with those numbers 2 and 5. And then we want to clean it up a little bit. So if I distribute the negative 5, this would be a negative 5x plus 10. And then if I add 5 to each side, this would be the written equation of that straight line whose slope is negative 5 and it's passing through the point 2, 5. Okay, I know you've done this before, but this needs to happen very quickly without hesitation when you start having to apply this to a question which is in much greater detail. Okay, another way they could ask you to write the equation of a line, and I'm going to let this be number 2, would be write the equation of this straight line given 2 points, or not 2 points, yeah, given 2 points. Suppose your 2 points are the points 3, 7 and negative 4, 6. So in this case, they didn't give you the point and the slope, they gave you 2 points. But to apply the formula, you need the point and the slope. So you're going to have to figure out the slope. And I know y'all know the slope formula. Slope is the difference in the y's over the difference in the x's, which is also referred to as y2 minus y1 over x2 minus x1. I know that's bound to be very familiar. So this is going to be 6 minus 7 over a negative 4 minus 3, which is a negative 1 over a negative 7, which is a positive 1/7 slope. So the slope of a line passing through those 2 points, or the degree of slant, is a 1/7. Okay, so the slope is 1/7. So if we're going to use the formula, we need a point and we need the slope. Well, you got the slope to be 1/7, and the point is your choice. You pick whichever one of these points you want to pick. It doesn't matter. I'm going to pick the one that has all the positive numbers in it. Why not? So I'm just going to go ahead and use the 0.37. So then when you come in here and you apply the point slope formula for writing the equation of a straight line, it's going to be y minus y1, or y minus 7, equaling the slope, which is 1/7, times x minus 7. Did I do something wrong? 3. Too many 7s here. That's a 3. So this becomes y minus 7 equaling 1/7 x minus 3/7, y equaling 1/7 x minus 3/7, and add the 7, which is going to be adding a 49/7 to get those denominators the same. So you get y equaling a 1/7 x plus, what, a 46/7? Not a very pretty equation, but there it is. So again, this is information that you should already know, information again that I hope you can recall very quickly and with confidence as we move further into this chapter and we start talking about writing the equation of a tangent line to a curve. That's all you need to do. Okay, so that's a little bit of a review. Now the other stuff we also need to talk about is a little bit of new stuff. So I'm going to put on here the word new. A little bit of new information. We're going to start going now really in depth, or a little more in depth, into section 2.1. And take a look and see what in the world they're wanting me to learn in this section. I'm actually going to pull the book in front of this camera and look at page 39 of the textbook. And again, you can access this very simply through My Math Lab. Okay. Here it is. It's a lovely paragraph of information. It's very well written right here. And this is, you can see the little title, section 2.1, rates of change in tangents to curve. Calculus is a tool to be understood, blah, blah. When you start with the in this section, it says in this section we introduce the ideas of average and instantaneous rate of change and show that they are closely related to the slope of a curve at a point on the curve. So when we start talking about instantaneous rate of change or average rate of change, you're talking about the slope between 2 points on a line. So average rate of change and instantaneous point of change are slope values. And so that's our goal, is to kind of find these slope values along a line, at points along a line. We get precise developments of these concepts in the next chapter. But for this section, we're going to use some informal approaches, kind of look at it and talk about it, the concepts involved, not getting too deep into it just yet, just kind of getting a touch of it, so that later when we get into it, it will lead naturally into the main idea of the chapter, which is actually the limit. So we will see limits play a major role in calculus as we move forward. So we're really going to be talking about rate of change, or instantaneous rate of change, which is really the slope. And then it's going to grow into talking about limits. So they're kind of giving you a little bit of an overview here, which is nice, and prepping you for what's going on in this chapter and in the early parts of calculus. So now, when we talk about that, what we're really talking about is a curve, and a tangent line to a curve. Okay, so we're really talking about a curve. You hear the word a curve, and when you talk about the curve, that's really your original function. The curve is your original function, or your original polynomial. And you know, that doesn't seem like that could be difficult, but it gets difficult because it starts getting a little confusing. So remember, your curve is your given original function, and usually it is a curve, it's not a straight line, which is also your polynomial. And what we want to know is the slope of the curve at a certain point. So for instance, let me see if I can do this in pen. Let's put a curve up here. In fact, I'm just going to sketch something like a parabola, okay? That is my curve. Okay, where is it? I guess I should project it well. Okay, this is the curve, or the polynomial, or the original function. What we want to do is find the slope along the curve, which means I wonder how slanted the curve is around here versus here versus here. I wonder what the approximate slope of the line is in those very detailed regions of the graph. So we come up with trying to figure out the slope. Well, if you take a look at this point, if you draw what would be referred to as your tangent line to the curve at that point, then that would be an approximation of the slope of the line at that select point, which would be a negative slope. If you were at this point on the curve of your parabola, the vertex of your parabola, and you drew a tangent line to the curve, it would be a horizontal tangent line, which would probably have about a slope of 0 down there at that vertex. So the slope of the tangent lines varies as you move along the curve, which is what they were talking about when we were talking about finding rate of change along the curve or instantaneous rate of change at a point on the curve. So these are tangent lines. So in other words, when you're looking for the rate of change at a point on the curve, the rate of change is changing. It's different here and here and here and here and here. On every point of the curve, the tangent lines have a different rate of change, a different slope. And that's really what the goal is when we're moving into this section, is coming up with the slopes of those tangent lines, or the instantaneous rate of change at a point. Okay, so this is where we're going. So if you start talking about the slope, we're also considering the rate of change equaling the slope, and we're talking about the slope really of these tangent lines to the curve. Okay, and when we do this, the slope and the rate of change of the tangent lines, this will eventually grow into limits. And limits become we get really pretty deep into limits by the time we get into the next section. Okay, so find the slope or the rate of change of the tangent line at select points along the curve. Okay, that's kind of where we're headed. So the curve is the parabola. The tangent lines are all those straight lines that are tapping the line at a select point. Okay, so now let's talk a little bit more about the tangent line. That's kind of a review. I should call it review and new. Review and new, kind of old stuff and kind of what you're getting ready to learn stuff in that part A. And I do tend to give rather organized notes. Try to. They might not be very cleanly written, but they should be well organized. Okay, so now we'll take a look at part B and we'll talk about the tangent line. Now that we've introduced it, now we're going to talk about it a little bit. I'm also going to refer now back to the textbook, and I'm going to look at page 42. And I'll try to always remember to put the page number on there rather than just throwing the book under the camera. Okay. And let's take a look at this figure 2.3 with all these lovely red and blue lines. Okay. Myself organized up here. All right. It says, take a look. Let's just kind of read the title of this figure. It says, the tangent to the curve at P. So you're looking for the tangent line at P. The tangent to the curve at P is the line through P, whose slope is the limit of the secant slopes as Q. And when you see this Q arrow P, that means as Q approaches P from either side. Let me see if I can focus this a little bit. Wow, that's a lot of words. Okay, let's stop and think about this. If you need to find the slope of a line, you have to have 2 points, right? So rather than just tapping the line at P and trying to find the slope of that red line, I only have P, the 1 point. I need 2 points to find slope or rate of change. So we create a second point like over here, okay, which would not be very logical, but it's an option, okay? And so if you create another point along the line, and I'll try to kind of highlight this. So you're looking at this line here. This is a secant line to the curve. And so if we used that secant line to get if we took the slope of that secant line, we're kind of estimating what might be the slope of the true tangent line at the point P. So we would find the slope of that first secant line, so that's pretty lousy. So then we would pull a point a little closer to P and come up with this line, another secant line. And we would choose those 2 points, which would be point P and another point at the tip of that red arrow. You use those 2 points to find the slope of that line, that secant line, and say, well, that's better than the first estimate, but that's still not very good. So you keep getting these secant lines, getting 2 points on the line until you get closer and closer to the real tangent line. But we play with secant lines because we have to have 2 points to determine the value of slope, to use the slope formula, which is going to give us that rate of change until we finally get to the true slope of the tangent line, which we're going to find using methods as limits and so forth and so on to get there. So now when it says the tangent to the curve at P is a line through P whose slope is the limit of the secant slopes as Q approaches P. Okay, Q are all these points that gives you the second point of the secant line. So as Q moves closer and closer to P, then your slope of your tangent line becomes more and more accurate. So as Q approaches P from either side, the slope of your secant lines is approaching the true value of the slope of the tangent line, which is really our goal. So you're going to play with secant lines a little bit. And then up here above the diagram it says, to define tangency, we need to take an approach that takes into account the behavior of the secant lines. And remember, P is the point that we really want the line of tangency going through, and Q is the other point that's creating the secant line. So as Q moves toward P along the line or along the curve, we get more and more a better accurate value of what might end up finally being the true slope of the tangent line. Okay, so that's kind of hopefully giving you a little more understanding of what's going on here. We're going to use secant lines to try to predict the slope of the tangent line. Okay, so again, you're going to hear me really kind of flip with these words or use these words interchangeably. The average rate of change is the same thing as really the slope of the line. The average rate of change is going to be the same thing as the slope of a line. Now, let's get a little bit of notation in here. In fact, you're going to see some pretty thick function notation. I hope you're very comfortable with it. And we're going to again go back to the textbook and look at figure 2.1 on page 41. And I'm also going to copy. In fact, I'm just going to kind of do it myself. But this is what I'm more or less trying to duplicate is the figure in the book. But I'm going to sketch it so that we can discuss it at length. So, we're going to put a curve up here. Suppose my curve looks something like this. And I don't know what the rest of it does, but there's part of a curve. Okay? And suppose I want to try to find the tangent line to the curve by using secant lines and slopes of secant lines. So let's get a little bit of notation. If I pick this point, I'm going to identify a couple of points on the line. And if you're not on graph paper, that's fine. Don't worry about it. But I kind of need to use it so that at least it's displayed to you relatively well. Suppose this is point x1, my first x, and this point is my x2. And if I'm going to find the slope of the secant line through these points, and I'll go ahead and draw the secant line. Okay, if I want to know the slope of that secant line, okay, then the way I would write it is I'm looking for the average rate of change, which I know you have seen written as delta y over delta x, the difference in the y values over the difference in the x values. Now, the name of this point algebraically, your x value is x1, and your y value is f of x1. The ordered pair of the second point is x2 and f of x2. Okay, that's your notation for your x, comma, y. It's not autofocusing very well. So when I find the average rate of change, which is the same thing as slope, I take the y values, which was f of x2 minus f of x1 over the x values, which would be x2 minus x1. That is your slope formula, y2 minus y1 over x2 minus x1, using the function notation, f of x2 minus f of x1 over x2 minus x1. Now, what they commonly use in our calculus book to represent that horizontal distance between x1 and x2, they say, let this be distance h. So if I let that be distance h, then this becomes f of x2 minus f of x1 over h. Okay, over h. Now, one more thing. If that distance between x1 and x2 is h, then x2 could be rewritten as x1 plus h, right? x2 is x1 plus, this distance x1 plus h makes the distance of x2 from the origin. So I can replace the notation of x2 with x1 plus h will get me back to this horizontal location. So everywhere there's an x2, I'm going to replace it with x1 plus h. So this becomes, this x2 will be replaced with x1 plus h. So this becomes f of x1 plus h minus f of x1 all over h. And that's what you will see written many times in your textbook. Let me see if I can find it. You're going to be seeing h used a lot in your formulas, and here it is. It's written on page 41 in this lovely little blue box. The average rate of change, which is your slope, all that is slope, is going to be your y2 minus your y1, which is going to be replaced with x1s and h's. And you're going to see this many times over. Here's the diagram that I just pretty much duplicated in your textbook, again on page 41. Okay. So the average rate of change is going to be the slope of a secant line, and we want it to get closer and closer to the tangent line, which really means we want that h to be really small, which is going to take us to limits as we move through this information. All right. So let's do some examples. This is really quite easy now. Average AVG. You're extremely quiet. I haven't taught for like 3 or 4 weeks over Christmas break, and my voice, I can tell, is already a little bit weak. It's the most unreal. All right, so let's take a look. Let me see. At average rate of change, and I'm going to go straight to the textbook, and I'm going to actually do example number 2, which is on page 44 of the textbook, which is the exercise portion of the textbook. So let me just show you the question. Get it up here on the camera, no big deal. Okay, this is very easy. It says, find the average rate of change, which is slope, find the slope, okay, of the function over the given interval or intervals. Okay, find the average rate of change, which means just find the slope. You can figure out slope over the given intervals. Okay, and this is what number 2 says. I think I'm going to have to get that table a little bit closer to me. Okay, here's what number 2's function is. It is g of x equaling x squared, and then it gives me this lovely little interval. So it's telling me to find the average rate of change of that function using this interval. Okay, to find slope we need 2 points. This is not a point. This is an interval. These are x values. This is like your x1 and your x2. This is interval notation. So your 2 points are given in this interval and only giving you the x value. So your 2 points, one of them is the x value is -1, and the other is your x value is +1. Those are your 2 points. So you're pulling your x values from the interval notation. What are the y's that go with the x's? Well, go to the function and figure out what they are. So what's going on here graphically, this is a parabola. It should be going through the origin. I just missed it. Okay, and you're going through the point -1, and the other point is 1. So this is the point 1 something, and this is -1 something, and we're finding the slope between those 2 points, or the slope of the secant line to the curve going through those 2 points. So if x is -1, you go to the function, g of -1 is -1 squared, which is a +1. If your x value is +1, g of 1 is 1 squared, which is also +1. So those 2 points are -1, 1, and 1, 1. There's your 2 points that you're looking at the slope between. So your average rate of change, which was the question, is just to find the slope between those 2 points, which will be y2, if this is x1, y1, and this is x2, y2. It'll be y2 minus y1. I guess I better write that. Okay, so it'll be 1 minus 1 over 1 minus a -1, which will be 0 over 2, which is 0. So we're saying the average rate of change, or the slope of that secant line going through those 2 points on the curve, is a slope of 0. There's no change. That's what they're saying. That's how you do it. These are very easy questions. You just have to learn how to read the question. That's like the first part of the question. They gave a second interval on this same question in that question in the book, where the second interval was -2 to 0. Okay, this was the second question. So this was like part A of the question and part B. There were 2 questions involved. This is the second interval. So if I want to find this one, I'm looking at the point -2 somewhere over here, and the point where x is 0 here. So these 2 points are -2 something and 0 something. So here's your 2 points. If x is -2, -2 squared is 4. And if x is 0, 0 squared is 0. So these 2 points are -2, 4, and 0, 0. You're looking for the slope of the secant line going through those 2 points to the curve. So the average rate of change is the same as the slope, which will simply be the y2 minus the y1 over the x2 minus the x1. So it's 0 minus 4 over 0 minus a -2, which is a -4 over a +2, which is a -2 slope. And that's also very obvious graphically. I can get all of it on the screen. If I drew that secant line, the slope of that secant line, the average rate of change between those 2 points, that is a negative slope, a -2 slope, a -2 rate of change. This is not difficult. Your challenge will be to understand that this notation, this -2, 0, the square bracket notation, this is an interval. And it contains the x values of the 2 points that you're going to create the secant line going through. That is your interval, and then you just need to be certain you pull those x values to create the 2 points to come up with the average rate of change in those 2 questions. Not difficult at all now. Y'all should be able to do this very easily. Okay. I'm going to put another one up here and have you work it. So this is your first example. Part B will be your second example, and I'm going to step back and make certain you are comfortable with that notation. So let the next question be. Anybody get an answer? 17? Somebody got 19?
I got 19.
We are close. They're both odd numbers. They're both prime. Okay. All right. Let's see what's going to happen here. Let me get the recorder back on. Okay, so let's take a look at it. Have some variation of answers out there. So, this is 2 points. One of them has an x value of 2, the other has an x value of 3. If x is 2, 2 cubed is 8, and 8 plus 1 is 9, right? 3 cubed is 27, and 27 plus 1 is 28. So our average rate of change, which I keep writing this because I know you're gonna see this word everywhere, which is the same thing as slope, is going to be 28 minus 9 over 3 minus 2, right? Which is, isn't that 19 over 1? Okay. So I think the correct answer is 19. Okay. So I didn't bother to graph. This is a cubic function. Lifted 1 unit, something like this, right? So between the point 2, 3, so sort of like here and here, if you drew that secant line, the slope of that secant line would be approximately 19, a pretty dramatic rate of change. Right? That's kind of the way that's working. All right, so it should have been 19. So if you got 17, you might want to take another look at that. Give it a little more time. We also need to look at an example very quickly that has a little bit of trig in it. We're still doing the same examples. I'm actually still pulling this one directly from that same set in the textbook. But this time they gave me the function to be a trigonometric function, 2 plus cosine t. So here we have a trigonometric function, and the range is between 0 and pi, the interval. To remember, the interval in those square brackets is the x values of the 2 points where we're trying to create the secant line and find their slope. So there you go. So now, what is if the x value is 0, what is the y? Well, g of 0 would be 2 plus cosine of 0. Cosine of 0 is 1, so 2 plus 1 is 3. So that ordered pair is 0, 3. Okay? If we put in pi, g of pi would be 2 plus cosine of pi, and cosine of pi is a negative 1, so that matches a 1. So there's your 2 ordered pairs. Those are the 2 points on the curve that you're going to put a secant line through and find their slope, which is the average rate of change. So the average rate of change, again, is the same thing as slope between these 2 points, is the y2 minus the y1 over the x2 minus the x1, which is going to be a negative 2 over pi, or a negative 2 over 3.14, about a negative 2/3 slope of that secant line of that trig function going through those 2 points. Okay. Now, another thing we're going to run into, really the big thing in this section is getting used to the notation, like the intervals here. You're going to play around now again with h, and so we need to kind of look at this notation with h. We're going to really be doing the same thing, but just as I probably shouldn't have, I didn't write y2 minus y1 over x2 minus x1 and fill in the, all those variables, all the notation. It gets a little thicker when you start playing around with the h, and so we want to get a little, it's going to get a little more algebraic, but the concept remains the same. So let's take a brief minute now. Let's go ahead and let's take a look more at the tangent line to the curve. And we're going to play a little more in the notation. The notation is going to get a little more hairy. Okay. All right, so I'm going to go directly to looking at this example in the book, example 3 on page 42. And I'm going to make this kind of lengthy, or kind of slow, I guess you could say, because the notation gets kind of difficult to follow. And I want you to realize that the notation is not that big a deal, and I want you to be able to understand it. So on page 42, it says, and I'm going to do it just like the book, right here at example 3, find the slope of the parabola y equaling x squared at the point 2, 4. Write an equation for the tangent to the parabola at this point. And you can see very quickly here, what is all this mess? Okay, look at all these h's they're throwing in here, and they're really not explaining what they're doing or how they're doing it. But there's a lot of algebra going on there that we need to think about. Okay? Note here, it doesn't say find the slope of the secant line. We're going all the way. We're finding the slope of the tangent line at one point, 2, 4. Okay, so it's not giving me a second point. It's not giving me an interval of values here. We're taking it in greater depth to find it a little more accurate this time. So we have a parabola. And it's just the basic parabola, y equaling x squared. I mean, they've not done any kind of transformations to it. They want to know the rate of change of the parabola at the point 2, 4. Give me the slope of the tangent line to the point, to the curve at that point. Then what they wanted me to do is they want me to write, okay, the question is, write an equation for the tangent to the parabola at this point. Write the equation of the tangent line to the curve at this point. Because every tangent line is different all along the curve at every point on the curve. Okay, so what in the world's going on here? Okay, so let's try to get a visual of this, a graphical visualization of this. This is just a typical old parabola. Nothing's happened fancy to it. But we're looking at the point 2, 4. Suppose this is the point 2, 4. Okay, I'm just putting a dot on there and claiming it 2, 4. We are looking for this tangent line to the curve. And I'm going to be a little more like so. Okay. Now, if we're ever going to find the slope of anything, we have to have 2 points. So what we're going to do is say this is where the x value is 2, and we're going to go a distance of h to another point over here, who will be 2 plus h. So that we do get a second point up here off the line, but there will be a second point that we're really going to work with. So we're going to kind of fake another point and let it be h units away from 2. I probably shouldn't have drawn it quite that far away. So my 2 points, even though I'm right in the middle of all my written work, this will be my second point. This first point is point 2, 4. This point will be the x value 2 plus h, okay, because I'm h over from 2. H units added to the x value to the right. And then what will be the y match to that point? Anybody know? There you go. F at 2 plus h. I wrote like the book, y equaling x squared, which could have been written f of x equaling x squared. So this point, this y value, and I didn't leave good space, is f of 2 plus h. So your 2 points, and I'll clean it up, your 2 points are 2, 4, and 2 plus h, f of 2 plus h. Those are the 2 points we're going to use to try to come up with the slope of the tangent line to the curve. So what is this? 2 plus h and f of 2 plus h mess. Okay, well, we'll make this happen easy enough. So the average rate of change is the slope, which is the y2 minus the y1 over the x2 minus the x1. So if we take the y2 minus the y1, delta y, this would be f of 2 plus h minus 4 over the x minus the x, which is the 2 plus h, minus the 2. That's the y2 minus the y1 over the x2 minus the x1. That's just slope. That is simply slope. See that little m right there? Okay. That is slope. They're just not perfect little numbers. So now we got a real issue. What in the world is f of 2 plus h? Well, that's easy function notation. If f of x is x squared, then f of 2 plus h is 2 plus h squared, right? And 2 plus h squared, when you expand that using FOIL, is 2 plus 4h plus h squared. So f of 2 plus h is 2 plus 4h plus h squared. So now, this information is going to replace that f of 2 plus h in that awful looking fraction or rational. Okay, so this now becomes, replace the f of 2 plus h with 2 plus 4h plus h squared. Okay, lots of h's, and remember, I'm telling you, you're going to see h a lot when we go in through this chapter. Yes? Yes, it should. Thank you. Thank you. Okay, that's a 4. It's really ugly now, but... So what does this equal? This is going to simplify quite nicely, because the 4 minus the 4 is no 4 anymore, right? 4 minus 4 zeroes out. So this becomes 4h plus h squared. On the bottom, 2 plus h minus 2, the 2's zero each other out over h. And this should really all play well for you when you're doing this. This should happen consistently, that the numbers kind of add out as 0. And then what you have is in that numerator, if you take and factor an h out, that's a common procedure. You want an h to factor, because then you get to reduce, and you come up with the average rate of change to be 4 plus h. So how in the world did we go from that simple little slope formula in the last example to this mess? Okay, it's the same. You just have function notation involving lovely little h. So let me talk just a minute. All they gave me was, it's a standard old parabola. I want to know the rate of change at 2, 4. Pretty much give me an informal idea of what the slope is going to be at that point. So we put the 2, 4 on there. We throw another point, because you've got to have another point to compute slope. We throw another point into the picture by letting it be h units off of 2, which gives us the ordered pair 2 plus h, f of 2 plus h. So here's the 2 points that we're finding the slope from, just like we were doing in those last examples, but h is all involved. So now I find the slope, y2 minus y1 over x2 minus x1. I figure out what f of 2 plus h is and try to get it right. Then I clean it up, and then I get this weird result, okay, which is supposed to be the slope, the average rate of change at that point. Now, let me show you what the book has to say at this point. And the book does a much prettier diagram than me, okay. The book did all the same things we did and came up with the same result, h plus 4. Here's their much better picture of our work. Okay, it looks a lot better. Okay, it says if h is greater than 0, meaning the distance from 2, if h is positive, which means it's to the right of 2, which is the way we've got it here, then q lies above whatever. La, 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 okay. Then it says, here's the important part. Whether, it says, in either case, as q approaches p along the curve, q is this point that has the h added to it horizontally. As q gets closer to p, that distance h gets smaller. As q slides along the line and gets closer to p, the horizontal distance h gets smaller and smaller. So if we can get q as close as possible to p, then that line, that tangent line, should be a pretty accurate tangent line to the curve. So guess what they say? They say if h approaches a value of 0, meaning the point q is in unison with the point p, then the secant slope becomes 4. Because when the distance between the 2 points becomes 0, h becomes 0, and then the h plus 4 becomes 4. So we take 4 to be the parabola's slope at point P. In other words, we take 4 to be the slope of the tangent line at the point P. This is going to move into limits quite seriously. So if you can get the understanding of this concept, you'll do a lot better through this whole chapter. As h approaches 0, as this distance between these 2 points, this horizontal distance, as it gets smaller and smaller, Q will become closer and closer and closer to the point P, and the slope of the tangent line will become more and more accurate. When we finally just make a blatant statement, let h be 0, meaning that there is no distance between the 2 points, then we have the perfect tangent line to the curve. We have the perfect result of the rate of change at the point. So we let h be 0, which means 0 plus 4 gives me a slope at the point of 4. Okay? So right here, we all of a sudden make this informal statement, which is, I want h to be 0. Let h be 0. Means we're going to have informal accuracy, okay? And when we do, then this slope becomes 4, which means the rate of change at that point on the parabola is 4. So we found the rate of change. Now, I'm getting very messy here, and I need to move to another sheet of paper, so I'll try to do this as smoothly as I can. We got to look again at the question. The question, which I wrote very sloppily, okay, is write the equation of the tangent line to the curve at this point. So here comes, yeah, I wrote that poorly. How could I be that sloppy? I don't like to write. Okay. Okay. So we're supposed to be writing the equation of this line, this kind of dashed line. We're supposed to have the equation. If I want the equation, I might can actually fit it on here. If I want the equation of that tangent line at that point, I need the point, and the point was given to be 2, 4, and I just said the slope is 4. There's my point, and there's my slope to create the tangent line to the curve at the point 2, 4. So here's my equation. Y minus y1 equals m times x minus x1. So I get y minus 4 equaling a slope of 4 times x minus 2, or y equals 4x minus 8 plus 4, or 4x minus 4. There is the grand answer to the question. That is the equation of the tangent line to the curve, the tangent line to the parabola at the point 2, 4. Have I got all that? I'm sorry it's so messy. I tend to get kind of sloppy. Okay, so let's try it again. I'm not going to be quite so detailed or quite so slow on this next one. That's number 1 under part D. Let's do a number 2. Same thing, this different curve. Okay, suppose this time our curve is y equaling 5 minus x squared. And the point on the curve is the point 1, 4. Again, we want to write, let's see if I can write this a little cleaner. Write the equation of the tangent line to the curve at the point 1, 4. Okay, this is still a parabola. If we want a vision of this, y'all can sketch this very quickly and very easily. 5 minus x squared. Negative x squared is a parabola concave down, so this is up 5 units. Looks something like this. That's the curve. This is the curve. We have the point, say, 1, 4. We want to create a tangent line to that point. But to get a tangent line, we're going to kind of rig this second point. We're going to kind of rig this secant line using this h thing. So suppose I pick another point over here a little further to the right. then this is going to be 1 plus h. So this point is at 1, and the second point is over here, h units. So your x value is 1 plus h, and your function value is f of 1 plus h. Those are the 2 points, which are going to create kind of a ambiguous secant line to kind of get us where we want to be, which is trying to get an instantaneous rate of change at a point. Okay, so, this really should have been written in function notation to make this all work with all this lovely function notation in general. So those are the 2 points that I'm going to create pretty much a secant line for and try to close in on the true tangent line. So if I'm going to find the average rate of change between these 2 points, which is the same thing as slope, which is delta y, I guess I should be using this notation a little more, delta y over delta x. Then you have y2, which is f of 1 plus h, minus y1, which is 4, over x2, which is 1 plus h, minus x1, which is 4. So here's my 2 points, my y2 minus my y1, and my x2 minus my x1. That's the slope formula. Now at this point there might be a little confusion. What is f of 1 plus h? It's nothing fancy. F of 1 plus h says go to your curve, the function itself. Everywhere there was an x, you're going to put 1 plus h. So this becomes 5 minus 1 plus h squared. Going back to the name of the curve, the parabola itself, replacing x with 1 plus h. So this becomes 5 minus, when we expand this, let's see if I can get it right, 1 plus 2h plus h squared. So this becomes 5 minus 1, which is 4, minus 2h minus h squared. That is the value of f of 1 plus h, which is going to be substituted back up here into the formula for slope or average rate of change. And so because of lack of space, I'm just going to pull this down a little lower. So f of 1 plus h is this 4 minus 2h minus h squared. Okay, so just as occurred in the last, these constants, this 4 minus this 4 is zeroing out, which is giving a numerator of negative 2h minus h squared and a denominator of just h. You should be able to factor in h out of the numerator to cancel with that denominator. That's pretty common procedure. So if I factor out an h, it leaves behind a negative 2 minus h. These guys reduce out, and your average rate of change is a negative 2 minus h. Now, we kind of wave a magical wand and say, we're going to pretend h is 0 so that those 2 points are so close together that we're really looking at not a secant line anymore, but the true tangent line to the curve at that point 1, 4. So again, this is like waving the magical wand because this is going to become a limit in the future. So we're going to say let h approach a value of 0. And when it does, this becomes a negative 2 minus 0, or a negative 2, which we're going to claim the slope of our tangent line to the curve at that point 1, 4. So then to answer the fullness of the question, which is to have the equation of the tangent line to the curve at that point. Now remember, this equation changes at every point on the line. So this is the equation of the tangent line to the curve at the point 1, 4. We got the slope. We just determined through all those efforts that the slope of that tangent line should be negative 2. And we got the point 1, 4. So to write that equation, we're ready to go. We just use our formula, y minus y1 equals slope times x minus x1. So y minus 4 equals a negative 2 times x minus 1. y equals a negative 2x plus 2 plus 4. There it is. There is the equation of the tangent line to the curve at the point 1, 4. And we are doing some serious magical wand waving because it's going to become much more difficult and much more accurate when we finally learn how to take a limit. So like I said, there's doing all this informal representation of this in order to kind of get you just a little bit comfortable with it before it gets a little more difficult. Okay, so I feel comfortable now that you should be relatively confident in this work. And when you get into my math lab, that homework is generated by this book. It tries to, is as good as they can make it happen electronically. So the homework section I'm going to show you here in this hard copy of the textbook will be very similar to the homework you're going to see in my math lab. So this numbers 1 through 6, just a review of what we just learned, is where you're finding the average rate of change, and they give you an interval, which is really the x values of the 2 points you're going to use. Pretty simple stuff. Then you move over here, and it gets a little more serious. It says, use the method of example 3. This is all the h stuff to find the slope of the curve at the given point and then the equation of the tangent line at that very point. So these examples are the ones where you do what we just did involving that h and letting h approach 0 to take your secant line into the tangent line. Okay, so you're going to see quite a bit of that. Then they have this. This is not difficult, but they have some really simple word problems here. And you'll see some of this in your homework, maybe 1 or 2 questions. Like this one, this table says the profits of a small company for each of the first 5 years in its operation are given here. Here's the year, here's the profit. Plot the points representing the profit as a function of year. So you're going to make a graph, okay? You're going to make a graph of this, and you're going to graph it. And then it says, what is the average rate of increase between 2 of the points? So you'll pick 2 points like 2000, 6, 2001, 28, or 27, and you'll find this. You'll put it into the slope formula and come up with slope, which is average rate of change. Very straightforward. So don't let any of these kind of word problems throw you off. There's nothing fancy there. They're not really playing in the h kind of part of this section and getting the rate of change, so you don't need to get